in preparation for tomorrow's lab, let's go ahead and discuss this epoxy chalcone synthesis, as well as the epoxide opening, which we'll do on tomorrow. So on last week we did the epoxide synthesis, where we took the chalcone and we treated it with hydrogen peroxide and sodium hydroxide to give the epoxy chalcone product here as white crystals, and we recrystallized those from ethanol on last week. So here's the mechanism. We first start with hydrogen peroxide. When we add sodium hydroxide, that sodium hydroxide deprotonates the hydrogen peroxide and activates it for the reaction. So now we have the peroxy anion here, and then here's our chalcone. We bring in the peroxy anion, and you can see that how the cyclization happens. This pair of electrons from the alkene comes here. This pair of electrons from oxygen comes here, and then you break the OO single bond, which is a weak bond because of electron pair repulsion on oxygen. Here's the transition state, where you have a bond forming here, and then the OO bond breaking, and then here's our product. Alright, so let's move on to the procedure. You can look over this. I'll give you I'll let this slide stay up for a minute, but the key at the beginning of the procedure is to make sure that the chalcone is fully dissolved before adding sodium hydroxide or hydrogen peroxide. And also another key point is to maintain the temperature at 40 degrees and not to let the temperature go above 40 degrees Celsius. And so what this means is that while you're heating it, if you have to take it off the hot plate and put it on the bench top to cool it back down to 40, you can do that. Alright, so now let's talk about the epoxide opening. And one thing to note is that epoxides act as electrophiles. And so both the carbon-oxygen bonds are polarized towards oxygen. And so if I add a nucleophile, in theory that nucleophile should be able to attack either one of these two carbons. They're both partially positive, and open the epoxide to give me an alcohol. Alright, and the reason that epoxides are able to be opened in this way is because the ring, the three-membered ring here, is strained, and so because of that, we're able to open that ring up. Now we can do this two ways. The first way is we can use a nucleophile, where we do this in basic media or neutral media. In this case, the nucleophile is just sodium methoxide and then hydrochloric acid at the end to protonate the oxygen once the ring gets opened. Or we can do acid promoted ring opening, where in this case the epoxide shown, we first treat it with sulfuric acid to activate it, and then the methoxy group here from the methanol will attack and open the ring. And notice the regiochemistry changes. Alright, if you do it under basic conditions, the nucleophile is going to attack the less substituted side. If you do it under acidic conditions, then the nucleophile is going to attack the most substituted side. Alright, so here's both of these are the two mechanisms how that happens. And again, under acidic conditions, the most substituted side gets attacked by the nucleophile, and then under basic conditions, the least substituted side gets attacked by the nucleophile. And this follows an SN2 type mechanism, where you have backside attack of your nucleophile at the carbon oxygen bond. Then you break the bond to get here, and then you have a proton source. In a second step, you will just add like an acid or water to protonate here and give you your alcohol. Under acidic conditions, it's a little bit different. First, you protonate oxygen. When you protonate oxygen, you generate this molecule, where now the OH, the oxygen is protonated, has a positive charge. And so this probably follows an SN1 type mechanism, where first this opens, and now this will become a plus charge here, and then the methoxide can come in and attack. Right, so this is step 1, protonation. Step 2 is ring opening, followed by nucleophilic attack. And then in step 3, you just have a deprotonation here by the conjugate base from the sulfuric acid to give you your corresponding alcohol. Alright, so you can look at this as many times as you need to. You can also ask questions. Alright, so what about today? So the lab for today, we're going to take our epoxy chalcone and we're going to open it using the acidic method. So we're going to first stir with acetic acid for 1 hour. Then we're going to add either water or sodium methoxide to that mixture. And if we add water, we will get this ring opening where we get a diol, this ring opening product. If we add the methoxide, then we will get this ring opening product where we get a methoxy substituted alpha hydroxy alcohol, which is here. Alright, so let's see how this works. So here, if we would do an acid catalyzed, we're doing this in acetic acid. Here's acetic acid. Acetic acid gets deprotonated by the epoxide. You can see the arrows here. And then when that happens, I'm now here with a protonated epoxide that's activated for ring opening. So now, once this epoxide is activated for ring opening, if I use the sodium methoxide, here's the methoxide anion that comes in and attacks the epoxide. I open this ring. That comes in and attacks the epoxide. I open the ring here. And then, or if water, which is my other nucleophile, if water comes in and attacks, I open the ring also. And let's look at the two products. So with the methoxide attack here, right, I have the methoxy substituted ring opening product. And then if water attacks, then I have the diol. Alright, so we're going to do either one of these, and I'm going to determine which group does what, which procedure. Alright, so for the procedure, we're just going to weigh out 500 milligrams of epoxy chalcone, dissolve it in 25 mils of acetic acid, and stir it in a 500 ml beaker for an hour. Right? At the second step, you're either going to add 200 milliliters of water and stir for an hour, or you're going to add 500 milligrams of sodium methoxide and stir for 1 hour. And then you're going to dry, filter the solid, and then we'll dry it, and then next week we'll recrystallize it from acetone.